Call me crazy, but these days I'm more interested than ever in concepts like software quality and performance. I'm not entirely sure why, but I have a feeling they will matter a lot more over the next few years. And one thing we can probably agree on is that old software was often far more elegant and performant than what we build today, simply because it had no other choice. Sure, I agree that today's software has a certain degree of complexity baked into it, and a lot of companies are facing huge scalability problems that simply did not exist 30 years ago. But then you read about the roller coaster game, which was written in the 90s directly in assembly in order to support thousands of characters roaming in real time around the screen with actions dictated by a rule-based AI system. Or you find out that in the 90s the creators of Quake 3 built a unified event system, custom memory allocators, and a portable virtual machine architecture inside a multiplayer game that had to run on a computer with a few dozen megabytes of available memory. So, in this Monday morning review, we'll review some of the most interesting implementation details that made a multiplayer game from the 90s a better engineered piece of software than almost anything we ship these days. The best place to start is the overall architecture. At the highest level, Quake 3 was built around a shared engine runtime divided into common, server-side and client-side systems, with each part responsible for a clearly defined section of the game. The common layer handled the main loop, the event queue, networking, memory management, file access, and the platform-specific code required to communicate with the operating system. On top of that, the server subsystem owned the authoritative state of the match, processed commands from every player, applied the game rules, updated entities, controlled bots through the bot library, and periodically sent snapshots of the world to every connected client. The client subsystem ran on the player's computer and handled the other half of the simulation. It collected keyboard and mouse input, converted that input into commands, sent those commands to the server, and used client-side prediction to estimate the player's movement while the next authoritative snapshot traveled across the network. Once a snapshot arrived, the client reconciled its predicted state with the version produced by the server. This allowed the controls to feel immediate even when the connection introduced noticeable latency. Rendering sat inside the client side of the engine, although the game logic itself never accessed the graphics hardware directly. What's interesting is that before Quake 3, different types of input were generally collected in different places. Keyboard input had its own path, mouse input had another one, network packets were processed somewhere else, and time was read whenever a subsystem needed it. For Quake 3, John Carmack, who led the game engine development efforts, decided to route all of these inputs through a single event queue. As a result, every keyboard press, mouse movement, console command, and network packet was converted into the same basic event structure. That structure contains a timestamp, an event type, a couple of integer values, and, when necessary, a pointer to additional data. Carmack wanted to reduce the number of places where platform-specific code entered the engine and replace a collection of separate polling paths with one predictable interface. So, instead of allowing each subsystem to reach into the operating system whenever it needed input, the platform layer collected those inputs, translated them into engine events, and pushed them into a central queue for the rest of the game to consume. This immediately simplified portability because every operating system only needed to implement the code that captured keyboard input, mouse movement, network traffic, and timing information, while the higher-level engine continued to process the same event structure everywhere. The Windows version, Linux version, and any future ports could gather input through completely different native APIs, yet everything above that boundary received the same sequence of events through the same interface. The more important benefit appeared once every external input passed through a single location, because the engine could now record the complete stream of events into a journal. But before going into details, please let me tell you a few words about today's sponsor. Plural just released workbenches, allowing you to deploy configurable DevOps agents that can investigate alerts, diagnose infrastructure problems, and even open pull requests with proposed fixes. You can run them manually, on a schedule, or trigger them automatically via Slackbot or a webhook, and since they understand your infrastructure state, they can gather the relevant logs, inspect Terraform or Kubernetes resources, and produce a clear explanation of what went wrong. Everything runs inside your own cluster, and every proposed change still goes through a pull request for human review. So instead of spending hours investigating an incident or working through another maintenance ticket, your team receives a documented diagnosis and a reviewable fix. Back to the video, keyboard presses, mouse movements, network packets, and timestamps could be written to disk in the exact order in which they reached the game, then replayed later through the same event processing code. Including time in this journal was especially important because Quake 3 was a real-time simulation whose behavior depended on the amount of time between frames. Recording user input alone would still allow the replay to diverge whenever the clock produced different values, while recording time alongside the other inputs turned the entire session into a deterministic sequence that the engine could process repeatedly. The implementation of the queue itself was equally interesting because Quake 3 used a fixed-size circular buffer containing 256 event slots. The engine maintained two continuously increasing counters called the head and the tail. The head identified the position where the next event would be written, while the tail identified the oldest event waiting to be processed. When both values were equal, the queue contained no pending events, and when the distance between them reached 256, every available slot was occupied. Because the queue size was a power of 2, the engine could map each counter to an actual array position using a bitwise mask. Instead of repeatedly resetting the counters or calculating a modular operation, it used the lower 8 bits of the counter to select one of the 256 slots. This produced a queue with a fixed memory footprint, constant time insertion and removal, and no need to resize or move existing elements during the main loop. The structure was simple enough to remain predictable under pressure, which mattered because mouse input, keyboard events, and incoming network packets could all arrive faster than the engine could process them. When the queue became full, Quake 3 discarded the oldest event to make room for the newest one. Before using that slot, however, the engine checked whether the event contained a dynamically allocated data block, which was commonly required for larger payloads such as network packets. The memory was released before the tail advanced, preventing discarded events from slowly leaking memory during an overflow. What's interesting is that the developers wrote the modules in C, but they compiled them through a modified version of the Little C compiler rather than the platform's normal native compiler. This compiler produced a textual intermediate representation for a simple stack-based machine, after which a tool called Q3SM combined the object files and generated a binary QVM module. The resulting bytecode made few assumptions about the underlying processor because operations were expressed through a virtual stack rather than specific CPU registers. When Quake 3 loaded the module, the engine could interpret these instructions or translate them into native machine code for faster execution. This architecture enabled a portable game module format that could run across every platform supported by the engine. A mode distributed as a QVM could work on Windows, Linux, and other systems without requiring the author to compile and maintain a separate native library for each target. So, Quake 3 runs on a stack-based bytecode VM with a just-in-time compiler and a sandboxed memory model. In other words, Carmack built his own Java virtual machine for the C programming language. That's what hardcore developers used to do back in the day. Damn! Portability, however, was only one part of the reason for building a virtual machine into the engine. The QVM also established a controlled boundary between the game code and the low-level systems around it, enhancing security. A game module could not directly call arbitrary renderer functions, access unrestricted memory, or reach into the operating system. Instead, it communicated with the engine through a predefined collection of system calls. Whenever the game module wanted to register a model, play a sound, read a file, or submit something to the renderer, it issued a numeric system call identifier together with the required arguments. The engine received that identifier and dispatched it through a switch statement to the corresponding native function. And, while all these are impressive, the bot system might be the most ambitious part of the entire project because Quake 3 needed computer-controlled opponents that could navigate complex three-dimensional arenas, choose suitable weapons, collect resources, retreat from dangerous fights, and coordinate with teammates while consuming only a small portion of the available processing time. They developed the Area Awareness System, which divided each map into smaller navigable regions and pre-computed the possible connections between them, including actions such as walking, jumping, crouching, swimming, teleporting, and using elevators. This expensive analysis happened when the map was compiled, allowing bots to find routes through a compact navigation graph instead of repeatedly analyzing the raw-level geometry during gameplay. Above the navigation layer, the bots used fuzzy logic to evaluate weapons, items, and goals. Rather than treating a weapon as simply suitable or unsuitable, the system assigned it a score based on factors such as enemy distance, available ammunition, health, and the bot's personal preferences. Each bot had different characteristics for aggression, accuracy, reaction time, and weapon selection, which allowed several bots facing the same situation to behave in noticeably different ways. The higher-level decision-making ran at roughly 10 updates per second, while movement and rendering continued at a normal frame rate, because tactical decisions never needed to be recalculated hundreds of times per second. The developers also experimented with genetic algorithms to improve the fuzzy parameters by allowing bots with different configurations to compete against one another, ranking their performance and using the stronger combinations to influence later generations. The result was a compact AI system built from pre-computed navigation, layered behaviors, and simple mathematical rules that still produce some of the most convincing multiplayer bots of its era. If you liked this video, you should consider joining our community where I'm posting more dedicated weekly content. Please don't forget to smash all the buttons, and see you in the next one!